use predictive modeling to train machine learning models and predict the outcomes or properties of experiments and molecules. Today I will be showing you how to quickly train a model with Suzuki Mira cross-coupling data and then use it to predict the outcomes of experiments that have not been run yet. I just downloaded some cross-coupling and antiospecificity data from a 2019 publication by the Burke Group at the University of Illinois at Urbana-Champaign. Here's the paper. I want to train a model to predict the delta-delta-G double dagger differentiating the retentive and invertive transmetallation mechanisms of a CSB3 cross-coupling. I obtained features for the phosphine ligands tested in this paper from the Kraken database, which was built by the Sigmund and Asparagusic groups. First, I will load a CSV containing features, or the X variables, and the target Y variable that we want to be able to predict. This is what that looks like. I also have the ID of phosphine ligands and their SMILE strings, and here are the features that I obtained from the Kraken database. If I scroll over to the right, you'll see where I have my delta-delta-G double dagger data. So let's start by creating a new workflow. Now I'll upload After uploading, you will be prompted to select the target variable from all columns of the CSV. In this case, it's delta-delta-G. And next, you'll be prompted to select all the features. So I'm going to select all, and then I'm going to deselect any of the columns that are not features. Now let's start by running a correlation analysis. This will tell us information about which features are most correlated with our target variable and which features are correlated with each other. Here you can see to the left a visual representation of the top 10 features correlated with delta-delta-G double dagger. Additionally, to the right, we can actually look at feature-feature correlations. So if we look at our basically best feature here, we can click it and look at other X variables that are highly correlated with it. And at this point, we can remove some of these, which oftentimes can build a more robust model if you remove highly correlated features. You can also calculate permutation importances for additional feature analysis information. Having gained a quick understanding of the correlations within my data, I will move on to model training. Under model parameters, I will first select the features that I want to train with. If I choose manual, all features that I selected above will be used to train the model. If I select auto tune, I will be given the option to input the number of features I want. Let's do 3. And this will utilize a fully automated feature selection protocol involving sequential forward feature selection with nested k-fold cross-validation that will identify the best combination of features. We can select which metric we want to optimize with the model. I'm going to choose mean absolute error. And for models that have hyperparameters, we can also tune them. We will start just by using simple linear regression because this is kind of a relatively small data set. Press train model. Okay, now to the left, we are visualizing the train and test data for our model. So actually it looks all right. We can also visualize the cross-validation metrics via a box and whisker plot. And also you can look down here to see additional model statistics, including additional error metrics for the train and test splits. If you click model features, you can see which features were selected by the automatic feature selector to train the model. This model performed well, especially for a small data set, but let's try building a more complex model. I'm going to switch to XGBoost. And now with XGBoost, let's just increase the number of features and let's go ahead and also select auto tune for hyperparameters. What this is going to do is optimize the XGBoost hyperparameters through a grid search. Let's press train the model. Okay, it looks like the calculation has completed. And now if we take a look at the cross-validation results, it seems like this model is definitely overfitting. You can tell by the big difference between the train and test and the cross-validation. But honestly, it's not as bad as I expected. You can see again the features that were selected for the model, and we can go ahead and now print some model statistics. So actually, if you look at the R squared, right, it's significantly worse than the test data is significantly worse than the training data, right? So this is definitely representing a model that's overfitting. Let's switch back to our simpler linear regression model by clicking here. This will save all of the previous models you've run so you can quickly switch in between them. Let's move on to making predictions across the Kraken phosphine database to identify potential high-performing ligands for the reaction. To inference the model on new molecules, I will upload an inference CSV that contains their molecular features. I can also press load inference file to inference on previously uploaded data. Press run inferencing to make predictions. I can see a list of predicted delta G double dagger values and the molecule's SMILE strings here. I can also visualize the structures of top molecules by pressing modeled molecules. To the right, I can analyze a histogram showing the distributions of predictions. Press download predictions for a spreadsheet containing this data. The same process can be used to predict other experimental outcomes such as reaction yields, properties of materials, and more.